This problem is from the 2025 Harvard MIT Math Tournament. Feel free to give it a shot and keep watching to see the solution. Okay, so here's how to do it. So they say compute the number of ways to arrange the numbers 1 through 7 in a circle. I'm going to draw the circle first. And okay, so 7 numbers, I'm going to put 7 blanks for the 7 numbers. So 1, 2, 3, 4, 5, 6, 7. And we're going to be putting a number in each blank, and they have to be from this list. You can only use each number once. Okay, and they're saying the product of every pair of adjacent numbers on the circle is at most 20. So what does this mean? So basically what they're saying is, so product means multiply. Multiply every pair of adjacent numbers. Adjacent means they have to be next to each other. So if I multiply this number and this number, it has to be less than or equal to 20. So this is one pair of adjacent numbers, but it says the product of every pair. So here's another pair of numbers that are next to each other, that are adjacent to each other. And this times this also needs to be less than or equal to 20. Okay, this times this also needs to be less than or equal to 20. And we can keep going. This times this times this also needs to be less than or equal to 20. Okay. And what does the last part mean? Rotations and reflections count as different arrangements. Okay, so basically, let's say we find an arrangement that works. I'm just going to say it's like this. You can check that this works. This times this is less than or equal to 20. This times this is less than or equal to 20. And you can keep going on your own to check that this works. But okay, so let's say we find something that works, but we can get another arrangement by rotating each number. Rotating by one number clockwise, for example. So if I move the 7 here, it's going to go here. If I move the 2 here, it's going to go here. And if I move the 5 here, it's going to go here. Okay, so we're just rotating clockwise. 3, 6, 1 would go on top. Okay, so basically what they're saying here is, okay, in some problems, this is considered as the same as this. These are not considered as different ways of arranging. But for this problem, they're saying that it does count as a different way. So this and this are considered different ways of arranging the numbers. Okay, and the same thing applies to reflections. So, for example, with this, I could have reflected the numbers. I could have reflected the numbers across some line here. So, okay, let's get another sheet of paper. Okay, so seven would go here, but we're reflecting across this line. So that means 2 would go here, and then 1 would go here. Okay, and let's do it with these two as well. So 5 would go here, and 6 would go here, and then 3 and 4 get swapped as well. Okay, so basically, if this works, this also has to work. Now, some problems, they say that this is the same as this. These are not different ways of arranging. But this problem says that it's also considered as different arrangements, because reflections are different and rotations are different as well. So yeah, so this is a rotation and this is a reflection. Okay, and they're considered different, so let's keep that in mind when before diving in. But that's the problem. That's what they're asking for. So how do we solve it? Well, with these kinds of circle problems, arranging numbers around a circle, if you compete, it's a common trick to take advantage of the symmetry. So what does this mean? Well, first off, what does symmetry mean? Symmetry means, well, there's rotational symmetry here, right? We can rotate valid configurations to get new configurations. We can also reflect valid configurations to get new configurations as well. So that's what I mean by symmetry, and we want to take advantage of it. Okay, I'm gonna get another sheet of paper. So here's what taking advantage of symmetry looks like. So we'll start by taking advantage of the rotational symmetry. Okay, so 1, 2, 3, 4, 5, 6, 7. For 7 numbers, and we need to use 1, 2, 3, 4, 5, 6, 7. Okay. So let's say we count the number of ways when 7 is here. That's also this is the same number of ways as if we started with 7 here. It's also the same number of ways if we started with 7 here. We could have started with 7 here and still be the same number of ways, and so on. So to take advantage of the rotational symmetry, we are going to count the number of ways when 7 starts here, and then multiply this count by 7 to account for the other cases. Okay. So there are 7 ways to place our 7 first. Why are we deciding to pick 7 to place first? Why not place 6 first? Or put 5 first down? Or 4, 3, 2, 1? Why does 7 have to go first? Well, this is another trick if you compete. Basically, you want to place down the number with the most restrictions. So what do I mean by that? Basically, place down a number where you minimize the number of subcases that you have to count afterwards. So 7 is the most restricted. Why? Because only 1 and 2 can be next to it. If you put 3 next to 7, it's going to be more than 20. But let's say I put something down like 1 first. Instead of putting 7 down first, I put down 1. Then you can literally put anything down next to it. So then you'd have to count the number of ways like this, count the number of ways like this, number of ways that start like this. And it's too many to count, so we don't want to do this. With 7, there are only 2 cases that you have to count. Actually, there's only 1 case you have to count, but here, I'll talk about it in a second. So, yeah, let's say we place down 7 first. Okay. Right, the only 2 subcases we have to count is if 1 goes here and 2 goes here, or if 2 is here and 1 is here, right? Because 2 and 1 are the only numbers that can be next to 7. Right? So from here, because numbers next to, every pair of adjacent numbers has to multiply to be less than or equal to 20. So this times this has to be less than or equal to 20. This times this has to be less than or equal to 20. So 7 is forced to be between 1 and 2. So these are the only 2 subcases we have to worry about. So it won't be as nasty as this, or you won't have as many subcases. like if you started with 1. So that's why we prefer putting 7 first. Try to minimize the number of subcases. But actually, we only need to count the number of ways where it starts like this. How come? What other kind of rotational symmetry can we take advantage of? Sorry, not rotational symmetry. What other kind of symmetry can we take advantage of? Well, we already took advantage of the rotational symmetry, so we can take advantage of the reflecting. So basically, the number of arrangements here that work is going to be the number of arrangements here that work, right? Because whatever works here, I can reflect across this line, and I'll get something that's like this, or something that has 7 here, 2 here, and 1 here. So, and vice versa, whatever works here, I can reflect across this line, and we'll get a valid arrangement that has 7 here, 1 here, and 2 here. Okay. So far, how many ways are there to place down our first 3 numbers? So there were 7 ways to place down the 7. And then there are 2 ways to place down 1 and 2. So 7 times 2 ways so far. Okay, what should we do next? What number should we place down next? So as a hint, we want to place down the number that has the most restrictions. So which one would have the most restrictions? 6. Okay, so we place down 6 because, well, it can only be next to what numbers? It can only be next to 1, 2, or 3. And we already placed down 1 and 2. Okay, so, all right, we'll focus on this case for now. Okay, so where does 6 have to go if it can only be next to 1, 2, or 3? So 6 can't go here, it can't go here either. Why? Because 6 has to be between 1, 2, or 3, right? But 1 and 2 are already used up. So I can put 3 next to it. Let's say we put 3 here. But then we run out of numbers to put next to 6. So that's why 6 needs to be next to 1 or 2. And then wherever we put 6, let's say we put it here, then 3 also has to be next to it. Okay. So, but you'll also notice that what has to go here, and are there any restrictions on it? No, we just have to put 4 and 5 here, and it doesn't matter how we put it, because regardless, this times this is going to be less than or equal to 20. This times this will be less than or equal to 20. This times this will be less than or equal to 20. Okay, so it doesn't matter how we put 5 or 4 there. Okay. So 7 ways to place down our first number, and then 2 ways to place down... Okay, 7 ways to place down our 7. 2 ways to place down 1 and 2 next. Okay. And then how many ways were there to place down the 6? Okay, I'll get another sheet so we can kind of replay what we just did here. Okay, let's see here. Okay, 7, and then what else? Okay, so without the loss of generality, we assumed that it started like this. 7 ways to place down our first number, which was 7, and then 2 ways to place down 1 and 2. It could have been like this as well, but okay, so 2 ways to place it down, 1 and 2. And then how many ways are there to place down 6 and 3? So 6 either goes here or here. But regardless of where we placed 6, there were always 2 ways to place down 5 and 4. But there were 2 ways to place down the 6 and 3, and then 2 ways to place down 4 and 5. It doesn't matter in what order you put them down. Okay, so the answer is 56.